Hello friends, I am Anirban Shah. Today we will learn Kirchhoff's law. There are two laws. The first law is the junction rule or the node rule. A junction is a point where three or more conductors meet. The first law states that the algebraic sum of the currents meeting at a point in an electric circuit is always zero. Now we have to follow some sign conventions. The first convention is that any current which is flowing towards the junction is positive. Any current which is flowing away from the junction is negative. So if you can see the diagram here, there are four currents. I1 is towards, so it is positive. I2 is away from the junction, so negative. I3 is negative. I4 is also positive. So the equation is I1 minus I2 minus I3 plus I4 is equal to 0. This was the first law. The second law states that in any closed part of an electric circuit, the algebraic sum of the EMFs is equal to the algebraic sum of the products of the resistances and the currents flowing through the circuit elements. It is also known as the loop rule. Now to elaborate more on the loop rule, we'll see a few sign conventions. There are other sign conventions. I'll give you a very easy convention. We have to remember that if any element would send a current from the higher potential to the lower potential, then we'll have a potential drop. For example, we have a cell or a battery. If we go from the negative terminal to the positive terminal of the battery, we'll have a jump in potential. The potential is increasing from low to high. So that EMF would be positive. If you go from higher to lower, then that EMF would be negative. If you go from higher to lower, as in for a resistance, the current would flow from high to low. So if we are traveling in the direction of the current, and then the IR product would be negative. If we are traveling in the opposite direction of the current, as in we are going from the low potential to the higher potential by traveling opposite direction to the current, so IR in that way would be positive. So in the loop ADCB, IR2 is positive. We are traveling anti-clockwise from low to high against the flow of the current, so it is positive. E2, again we are going from low to high, so it is positive. IR1, we are traveling from low to high, again it is positive. And E1, again we are traveling from low to high, it is positive, so which is equal to 0. Now let us solve a numerical, small easy numerical. Now this numerical, it says that you have to find the equivalent resistance between the point A and B. Now if you actually see, this looks like a Wheatstone bridge, but this is not a balanced bridge, because 2i's of R divided by R would be 2, and R divided by 2R would be half. So this bridge is not balanced. So now we cannot apply that Wheatstone bridge principle. So we have to solve this by Kirchhoff's law. Now if you look at the figure, we have assumed that a potential V is applied along A and C. So whatever current is flowing through the branches, so V by I, that ratio would be equal to the equivalent resistance. Let us assume I is the current flowing through the main branch EA. That current gets divided, as in I1 part of the current flows in the branch AB. So from the first rule of Kirchhoff, I minus I1 would flow through AD. Again, I2 part from I1 gets divided in the branch B to D. So in branch B to C, I1 minus I2 would be flowing. In the branch D to C, I minus I1 plus I2 would be flowing. So now we have the directions of current as well as the currents in itself in each branch of the circuit. Now we have three variables here, I, I1 and I2. So we need three equations to solve this. We have one more variable, that is V, but we can easily find out V by I, because we don't have to exactly find out V and I in absolute terms, but we can find out the ratio V by I. So three equations are sufficient. So if we take the loop ADBA, first let us go through the branch AD. We're going from a high to low, so it has to be negative. So the current flowing through is I minus I1, so minus I minus I1 within brackets multiplied by R. Then in the branch DB, we're going from low to high, so that would be positive. I2 multiplied by R. Then in the branch B to A, again we are going against the flow, low to high, so that would be positive twice R I1 equals to 0. So we have a reduced equation which is Ri minus thrice R I1 plus R I2 which is equal to 0. This is our first equation. In loop DCBD, minus twice R I minus I1 plus I2. This is the current flowing through DC branch. And again we are going from high to low, so that would be negative. But in the other branch C to B, we are going from low to high, so that would be positive. R I2 I1 minus I2. Then again in the branch B to D, we are going from high to low, so that would be negative. So we get this equation, the second equation, twice Ri minus thrice Ri1 plus 4 times Ri2 equals to 0. This is our second equation. So from these two equations, we can get the currents I1 and I2 in terms of I. So I1 is 2 by 9 I, I2 is minus 1 by 3 I. I leave this for you guys to solve. Then let us take a loop A, E, F, C, B, A, the external loop. So in this loop, we have two resistances and one potential drop. So we are going from high to low. So V would be negative. In branch CB, we are going from low to high. So that would be positive. I1 minus I2 multiplied by R. Again in the branch B to A, we are going against the flow. So that would be low to high and that would be positive. So I1 multiplied by twice R. So we get V equals to thrice I1R minus I2R. Put the values of I1 and I2 in terms of I, and then by solving we can say V by I ratio is equal to R equivalent, which is R by 3. I hope that you have learned a new concept today. Kirchhoff's law is very easy if you can figure out the sign conventions properly. Otherwise, a simple mistake can cost you very dearly, because these problems are very easy. Only the signs that you take will matter a lot. This is Anirban Shah signing off from Estudyz.com. Thank you very much. Please visit the blog cbsephysicsPune.wordpress.com/blog. Bye bye.